So hi, I'm Tim Tully from Menlo Ventures. I'm a partner here investing primarily in infrastructure companies. And with me today, I have Inception. I have Stefano, Aditya, and Volo. Welcome to Menlo Ventures today.
Thank you, Tim. Great to be here.
Thanks for having us.
Thank you.
Really just want to jump into your backgrounds first and foremost. So Stefano, you come from a small mountain village in Italy. It's a long way to come to Silicon Valley. Tell us a little bit about that.
Thanks so much for hosting us. Indeed, I grew up in a little village in the Alps, a very isolated place. Only a few hundred people live there. So I grew up, spending a lot of time outdoors, playing with my friends. But I was always very interested in building things. So I spent a lot of time with my dad, doing projects and stuff like that. Then I went to school in Italy and I studied engineering, of course. I was doing electrical engineering back then. But I sort of quickly realized that all the exciting stuff was happening in computer science. I'd been programming since I was a kid. I really enjoyed writing programs and do cool stuff. I had always been interested in AI. I still remember back in high school, I was trying to write software to do homeworks for me and stuff that never worked. But I was kind of very interested about building machines that can think, that can solve math problems, that can do interesting things. And so I went to the United States for a PhD in computer science at Cornell, studying AI. And back then it was not a very popular kind of topic. Everybody else wanted to do crypto and theory, and social networks were very popular back then. But yeah, I was very passionate about trying to understand how these systems work. And I did my PhD research on probabilistic models, probabilistic reasoning, which is kind of like a branch of machine learning that eventually became what we now know as generative models or generative AI. So I was kind of lucky because I started my PhD when people didn't pay much attention to that field, but then deep learning happened. And so by the time I graduated, it was one of the most exciting areas of machine learning and AI. And then I took a faculty position at Stanford. And then I've been here in the Bay Area for a while doing research in generative models, generative AI, including with Aditya and Volo, who were students in my group. And most recently, I've been working at Inception, scaling up some of the research prototypes, some of the ideas that we developed in my lab. And we've been kind of pushing the frontier of what's possible in generative models. We've been building these new kinds of language models based on diffusion that are much more powerful compared to what everybody else is building. And so, it's been an exciting journey from the little village where I grew up to the heart of Silicon Valley.
Yeah, absolutely.
Fun story.
And Aditya, you came from India all the way to Silicon Valley. What is your backstory?
Yeah, so I was born and raised in India. I was fortunate to have parents who prioritized my education a lot. So we got a computer in our home as one of my early toys that I can remember. And I also had an elder brother who made it fun by us spending a lot of time doing games on the computer. But then over time, I also got interested a lot in using it to build, starting with simple things like websites with HTML to then eventually also getting a lot addicted into thinking about low-level programming, especially in C++ and so on forth. So fast forward, I did my undergraduate in computer science at IIT Delhi. And soon after, I came to do grad school at Stanford, where I worked with Stefano, and Stanford has a rotation program where you try to find the best match of your advisor. And both of us were interested in probabilistic modeling, and our rotation project, in fact, was on doing variational autoencoders, one of the first generative models at the time. And it was very intellectually fascinating, and that's how I got into this field.
And Volo, you have a very interesting background. You were decoding genomes before you got into machine learning in this way. Maybe you can tell us a little bit about that.
Mm-hmm. So I was born in Ukraine, and I grew up in Canada, in Montreal. Did my undergrad in math and computer science at McGill, and I came to Stanford also for my PhD about around to 2012. This was a very interesting time, very different from how it was before in in Montreal. Very entrepreneurial. Everybody was building startups, and so I got pulled into that really quickly. And I got involved in my first year in a startup that was building a new kind of generative AI for biological sequences. I actually took a year off to work at that company, and we ended up building a really unique technology. It was commercialized by a big company later on. We published a paper on that in Nature, and that got me really excited to work on AI and applications in AI for science. And after a while, I came back to the PhD program, and then I end up working with a few groups on both AI for science, both the science aspect. So we built a lot of the early work on using probabilistic modeling over DNA sequences, genomics, but I was also really interested in the core aspects of machine learning, building algorithms that can learn. And after a while, I kind of gravitated towards Stefano's lab, where they were doing a lot of really cool work on generative modeling at the time. And I did some work there, and towards the end of my PhD, I got involved in a really interesting opportunity in applying AI and machine learning to reduce food waste in the supply chain. And so I took time off I went on another leave from Stanford for my faculty appointment at Cornell, and I spent several years building out a company which is called Afresh. It became so it's now operating in about 10% of U.S. supermarkets and playing a big role in reducing food waste. But ultimately, AI was a really big passion of me. So I eventually transitioned to chief technologist of the company for a couple of years, and at the same time, I started a research group at Cornell focusing on generative AI. And then over the past few years, we got really interested in diffusion for language. And then we realized, these algorithms can work really well. And I thought the next step in getting them to work and getting them to the real world was to start a company. And that's how I joined forces with Stefano and Aditya.
Got it. So you were doing a postdoc. Aditya, you were doing your PhD with Stefano. How did you guys know that you were the right team to pull this off and get the gang together? How did you know the Stefano? What did you see in the team, and what made you pull it together?
Yeah. So as you mentioned, Aditya was my second, I think, technically PhD student. So we've known each other for a long time. Volo was kind of like I kind of adopted him as a PhD student because his advisor was not around, and then he became a postdoc in my group, and so we've known each other for a very long time. The story is that I was working on diffusion for language in my group at Stanford. We were getting some really exciting results, and I knew that Volo in his group was also working on something similar and had published some paper kind of like following up on our approach. And I knew Volo had done startups before, so he was very familiar with how to set up a company, how to raise funding, how to run a small team and grow it into a successful business. And so he immediately came to mind as I really want to work with Volo on this. He's an amazing has an amazing technical background and also has like the entrepreneurial expertise that we need here. And similarly for Aditya, I mean, I've always felt that he's one of the best PhD students I've ever worked with. He'd done very relevant work during the PhD and also in his group at UCLA. I know the two of them had spent a lot of time together. They were like lab mates. They were sharing like the same office at Stanford, and so it felt like, okay, this is the right group that we need to put together. The early days of the companies, a lot of the focus is going to be on R&D, just like figuring out how to get this technology to work. And so we really needed like a very technical team and an exceptionally talented team. So then we can attract other researchers, other top engineers. And so that felt like the natural choice.
I mean, people are pretty familiar with the term diffusion. I think it's become a household name in a lot of ways, but I think a lot of people don't associate it with text generation per se. So kind of curious, was there an aha moment where you guys realized that diffusion techniques could be applied to text that sort of said like, hey, this is it, we're onto something, we have to start a company? Or did this come after years of research? Or just walk us through sort of how this materialized?
So we've been obviously studying this problem for many years, and I think it was a very obvious open problem in the field of generative modeling. If you look at the kinds of algorithms that are used out there, anything that involves images or video or any kind of continuous data, currently all of the methods, all the state-of-the-art methods use this approach that you mentioned called diffusion, which came out of Stefano's lab, and that works extremely well. This was the first wave of generative AI with things like Stable Diffusion and Midjourney. These are all based on this diffusion technology. But this approach only works, or for the longest time, only worked well for continuous data, images, videos, and for discrete data. The state-of-the-art approach has always been autoregressive models. And there was always an open problem in the field for how do you get diffusion, how do you get this modern approach to work equally well on discrete generation and language generation. And so we've all been studying this problem for many years, and there was a bit of a breakthrough around 2023, early 2024, with a lot of work that came out of Stefano's group with SED, the SED paper. So that was kind of a really cool result where the performance of these models was for the first time shown to be within reach of autoregressive models. And then also in my group, we've been researching an approach called masking diffusion, which was in part motivated by AI for science applications, so modeling biological sequences. We had grants on that, and that also seemed like the right approach for doing discrete data generation. And then when we tried it on a language, it also showed the same kind of great performance. And so we realized that now this could actually work, but we needed the resources and the capital and the team to make this happen and to actually show that this works at scale. So not on toy academic models, but on real production language models, we needed more resources, and that's what led us to start a company.
The one thing I would also add is, if you look at the history of language models in recent times, so there's been probably like 3 scaling laws that have determined progression. So there's been a scaling law around pre-training, there's been a scaling law around post-training, and finally test time inference. And diffusion is really unique because it offers advantages, especially when it comes to post-training and test time inference, that you don't see in autoregressive modeling. The reason is because when you have, let's say, trained a diffusion model, it's extremely fast. So you get about 5 to 10x speedups over autoregressive models. So there's post-training scaling law where, today most of post-training is determined by reinforcement learning, and reinforcement learning being bottlenecked by inference. If you had a really fast model, which you get with diffusion LLMs, we saw that in D1, and we've seen that's extremely powerful to scale these models, improve their quality, and that's how you can get a much better post-training routine using diffusion LLMs. And then the next thing that comes is that test time. How can you improve the quality of these models? There it's a similar approach. You have a faster DLLM that's going to search more in the same amount of time and get you higher quality. So across all 3 axes of quality, speed, and cost, diffusion LLMs dominate autoregressive LLMs. And that's how they can extend the frontier to a new technology that wasn't possible before.
Yeah, you mentioned reasoning. I think that's an important sort of monumental moment in the history of Inception. Talk a little bit about the Mercury 2 model and what that brings.
Yeah, so Mercury 2 is the first large-scale reasoning model based on diffusion. It's the world's fastest reasoning model as well in its class, and it gets extremely good trade-offs of quality and speed that were not possible earlier. And to come to this moment, we have taken 2 technologies at its very core, the idea of diffusion, training, and reinforcement learning, combine them into a single paradigm that is executed at scale to get to where we are.
Got it. And Stefano or Volo, one of you, what are some of the major use cases that you foresee with the reasoning and the speed that Mercury 2 provides?
Yeah, it's all about speed. People want their AI applications to go as fast as possible, and in some cases, like, it has to be fast to be useful. Like if you're building a conversational voice agent, like the answer has to be immediate, otherwise the conversation just doesn't work. Or if you're thinking about customer support, like the answers have to be quick. And there's a bunch of other applications where you're interacting in real time with a developer, with a customer, with a learner. And for all those applications, latency is critical. And what customers want is they want to have the best possible quality that fits within a certain latency budget. And what we've shown is that diffusion language models can provide the best-in-class quality for those kind of applications. And so that's where we're seeing the most traction right now. A lot of our customers are coming in because they want LLMs that are really, really quick and still good enough to provide high accuracy answers that then can provide a good user experience to their.
So it sounds like anyone that's out building agentic use cases or agentic workloads right now should probably be using Inception.
That's correct. And code is one vertical where these models are really good, and it provides a different kind of experience for the developer. If you're using a classical vibe coding method, maybe you give it a task and then kind of goes on and does something, and then it's usually not perfectly completed from the first try. And so you still have to instruct the model to make changes, and so you have this kind of slow iteration loop. If your model is really fast, then you can iterate much faster. You will still get an answer that will typically require a few edits, but then you can iterate on those edits much faster, and it's a much more satisfying experience for someone using these models for software development. And even beyond that, agents are now being used everywhere, from controlling a browser to let's say getting things done on the internet, booking a flight or anything like this. And the speed really matters for the quality of the experience that a user will get out of these agents.
And you guys mentioned speed often. What are we thinking in terms of speed? Like, how much faster than an autoregressive model are we really talking here?
Yeah, you can be up to 10x faster than a typical autoregressive model. So we're getting over 1,000 tokens per second. So that's the kind of speed that you would normally get only if you were to use a specialized AI inference chip. We can get those kind of speeds on GPUs, which means that we can support very large volumes, and the costs are significantly lower compared to special hardware.
Got it. And oftentimes when you think about autoregressive models, you think about transformers. How do people think about transformers and diffusion? Do they fall into the same conversation, or are they orthogonal from each other, or how should people think about that?
Yeah, this is a great question because it comes up often because people think of diffusion as an alternative to transformers when really they are extremely complementary. So we at Inception also use transformers, but we train them differently. So in an autoregressive transformer, you would train them to predict tokens sequentially one at a time. Here we are training these diffusion transformers to predict tokens in parallel. So we can inherit a lot of the benefits that have gone into building transformers as a dominant architecture for AI and supercharge it with the benefits that diffusion adds on top of it.
Got it. And Stefano, I think you have a really good analogy in terms of how to think about the parallel generation. What was that again?
Yeah, so if you think about the autoregressive models, it's kind of like a typewriter where you kind of generate left to right one character or one token, as we call it, at a time. And so that's a very kind of sequential computation where in order to generate something, you need to be able to generate everything that comes before it, and you're not able to look at things that are to the right of where the cursor is. A diffusion model works very differently. It works more like an editor, where you start with a guess of what the full answer should be, and then you refine it gradually in parallel by making it better and better. So under the hood, there is still a transformer model, but the transformer is not trained to predict the next token. It's trained to fix mistakes, to make your output better. And that's much more parallel because a single neural network evaluation is able to output or modify many tokens instead of just one. And so that's why our models are much faster, much cheaper. It's just like a better, more parallel solution that maps really, really well to GPUs and parallel compute hardware in general.
So going back to the creation of the company, all three of you had tenure track positions at really prestigious universities. What did you see? What caused you to pick up and put that on pause for a moment and start Inception?
Yeah, for me, it was that kind of seminal result that we had in my lab. There was this paper that we published where for the first time we were able to get diffusion models to be competitive with autoregressive models on text generation. That was something that everybody was saying, it cannot be done, and we were able to do it. And these diffusion models that we trained, they were still pretty small, like GPT-2 sized models, but they were producing results of similar quality to autoregressive models, 10x faster. And so I was just very excited about the idea of building something completely different. Like all the other big labs, they were all betting on the same kind of architecture. They are all more or less clones of each other. And there's this amazing technology that's going to change the world. And then you see everyone is kind of like building the same thing, and there's an opportunity to do something different. It just felt like, we have to see what happens if we scale this up. And unfortunately, it was just not possible to do it at Stanford. It just takes an amount of, basically we trained the biggest model we could, given the compute and the engineering capacity that was available in the lab. But in order to get it to the next stage, we really needed more compute, we needed more engineers, infrastructure. Like there's a lot of work that goes into producing a commercial scale diffusion language model. And the only way to do it was to start a company and actually build a team that is really pushing all together in that direction.
Yeah, so for me, it was during my PhD, I had also gotten a chance to spend time working at different research labs. I'd seen the early days of OpenAI, Google Brain, Microsoft, and Meta. So very, very different environments, all of them trying to bring AI to the real world. And what I learned from those experiences, in addition to bringing about new technologies through academia, was that if you really bring a group of people together to work on a topic within deep learning where there's really potential for success, resources can be extremely valuable. So that's why we started to think about how can diffusion be a paradigm that can be scaled. And in my own research group at UCLA, we had seen that diffusion for RL was working really well. So a lot of the research that I'd done following my PhD was at the intersection of generative models and reinforcement learning. And when I talked to Stefano and Volo, and we were talking about how diffusion for text could be a new paradigm, thinking about how that can then be brought to the real world by grounding it with reinforcement learning was an extremely exciting proposition. So that was how I personally thought about taking this plunge.
And for me, similar story. We've been working on diffusion in the lab in my group at Cornell, we're doing early work on mass diffusion for several years. And similarly, we saw that the performance was getting increasingly better and better and approaching and ultimately matching the performance of autoregressive models. And then it just became obvious that this could be a superior approach to generation that could actually work. At the time, no one really realized that we were at that breakthrough point. There were only a few groups in the world working on this problem, which were pretty much our research groups, and that just made it extremely exciting to have the possibility of have the kind of impact and move the industry to a new generation of language models. But of course, to actually make that happen, it is a lot of work, and it takes a lot of engineering effort, takes a lot of capital, a lot of resources, a lot of compute, and the only way to do this is by starting a company.
What are the next set of hard problems to be solved at Inception?
Yeah, there's still a lot of work to do in terms of like improving the quality, the speed, reducing the costs of diffusion language models. Still very early days. The frontier keeps moving, right? The other labs keep innovating, they keep improving their models. There's always new techniques that are being developed. And so, the frontier keeps moving, and we just need to catch up with them and then stay at the top. And so we spend a lot of time thinking about better ways of training diffusion language models, better ways of doing inference, like what is the right way to generate, what is the best way to generate text once you have a diffusion language model. Like it's not obvious. There's all kinds of improvements that can be made at the algorithmic level. Also a lot of work, like engineering work in terms of like really optimizing the algorithms for different kinds of backends, different kinds of GPUs, and which also matters at the end of the day as you think about the full end-to-end performance of the system. And those are pretty hard engineering problems because nobody has built these systems before, so there is still a lot of scientific problems, like just figuring out what is the right way of doing things. Also very hardcore kind of like engineering problems in terms of like building these systems, which are very complex. Like there's a lot of moving parts. And so it's really challenging and really interesting technical work that we need to do to stay at the frontier.
And there's also a lot of opportunity to bring about entirely new product experiences with these models. So if you think about some of the successful product that's come about even in the last few years, think about deep research. A deep research in 5 minutes versus a deep research in 5 seconds is an entirely different experience and capability that would empower users around the world in a very different way. So as we grow this technology and think about what product experiences this enables, interactive workflows where speed is a must-have, it's at table stakes. We are pretty excited about how these can be wrapped around delighting our users.
Yeah, and I would add that I think we're still in the early days of diffusion language models. They're already delivering an order of magnitude improvement over regressive models, but I still think we're in the early days. And part of that is the design space of what is a diffusion language model is much, much bigger than an autoregressive model. So when labs develop autoregressive models, they might make some certain tweaks in the architecture. Maybe they replace certain layers with Mamba layers or some other kind of architecture. But ultimately, it's still very, very similar. But if you look at the design space of diffusion language models, you still have the choice of architecture, but you also have the choice of sampler. You have the choice of what is a noising process, what is a denoising process. And I think right now at Inception with our technology, we are at a very, very interesting point in the design space. But overall, both at Inception and both in the field of in the field of diffusion modeling, we haven't yet explored the design space. And I think we're going to get to more order of magnitude improvements over to regressive models by further exploring the space with the research that we're doing at the company and the research that's being done right now in the field. I think there's very promising times ahead.
What is it like working at Inception Labs? How would you guys describe the culture of the company?
Yeah, it's still a fairly small, tight team. The talent density is extremely high. We have a set of really brilliant researchers and engineers that are, passionate about pushing the frontier of what's possible in the space of generative AI. It's still a very academic. I mean, the company started from academic research labs, and so there is still a natural curiosity that everyone has, and a tendency to kind of not take anything for granted, and sometimes make contrarian bets, and really just believe in data, believe in evidence, and be rigorous about the kind of experiments that we do, the kind of design choices that we do. So I feel like that kind of academic way of thinking about research, about the scientific problems that we need to address in order to build the next generation of diffusion language models is very, very strong at Inception.
Yeah, I think we have assembled a really focused and diverse group of people inside the company. So at Inception, we have a culture of thinking really end-to-end. So we think about how we're going to build these models, but we spend a lot of time as well how they'll actually deliver value to our users. And that kind of holistic thinking is also what enables us to bring about experiences and bring our models to market in a really fast manner. And overall, it creates a really fun culture where we all get to learn from each other every single day.
Yeah, and I would add that research is very, very much in the DNA of the company, and that's what makes us successful. We can out-innovate all the other big labs that are out there. I don't think there's anybody who's doing anything comparable to what we're doing, and that is because of this research DNA. In fact, almost everybody in the company has published machine learning papers at top conferences. I will even add that one of our two business employees also is a published author at NeurIPS. So it is very, very much in the DNA of the company, and I think that's what allowed us to be successful.
But you would hire people even if they didn't publish it. I mean, you can't hold that bar forever. I don't think.
If their GitHub is green, then for sure.
So if diffusion works the way you all believe it will, what does the world look like in 3 to 5 years?
Yeah, I see a future where all LLMs are going to be based on diffusion. Ultimately, the thing that matters is how these models scale at inference time. It's all become an inference game. You're seeing these massive investments in data centers, in infrastructure, in new chips, because there's going to be an enormous demand for LLM inference. And the solution that scales the best is the one that is going to dominate the market. And based on our experiments, based on our evidence that we have, diffusion LLMs are superior compared to autoregressive models. They Pareto dominate autoregressive models in terms of throughput versus latency. So for the same cost, you can get a model that runs faster. For the same speed, you can serve the models cheaper. You need less hardware, you need less, it will cost us less to serve the models. And so for that reason, we believe that everyone will eventually realize that this approach is better, and that we will see a switch from autoregressive architectures, which are memory bound, they don't map well to GPUs, they're very expensive to serve, to diffusion-based language models.
I would add that the real world is multimodal. So, and we already know that diffusion is the state-of-the-art technology for modalities like images, videos. And if you combine that with the breakthroughs we are making happen at Inception, it's very likely that we'll see this technology being dominant for all of AI. So unified models which combine language with these modalities can be extremely fast, high quality, and efficient to serve using these kinds of breakthroughs at inception.
Yeah, and I would like to add an analogy. If you look at the biggest breakthrough in AI in the last 10 years, I think we would probably say that this is the transformer. And so why was the transformer a breakthrough in AI? Before the transformer, we were training recurrent neural networks, or RNNs for language. And how does an RNN work? It generates, it operates sequentially, both at training time and at inference time. And so if you wanted to train and scale these models, the training was too slow because the forward pass was completely sequential. And so we had to move to the transformer to make training fully parallel, which then unlocked scaling laws for pre-training. And this is what led to language models and ChatGPT and all of these technologies. But then if we look at the inference of these models, it is still fully sequential. And so one way to understand diffusion, or one way to frame diffusion, is the corresponding evolution of inference from sequential to parallel. So I would say diffusion is to autoregression the same as what the transformer was to recurrent neural networks. And I think as diffusion becomes more widespread, we anticipate having the same kind of impact as the transformer has had on the field of AI by replacing RNNs. Similarly, diffusion will replace autoregression, it will make inference fully parallel, and will unlock new scaling laws like the one that we've seen for pre-training.
So guys, one of the biggest things that happened in the last 6 months is you had Mercury 2 come out, which unlocked reasoning within the model. Talk to us a little bit about what reasoning is, why it's important, and was there any specific technological sort of breakthrough that you had to make that happen?
Mercury 2 is the world's first reasoning model based on diffusion. It also happens to be the world's fastest reasoning model. And to get to where we are with Mercury 2, there were a bunch of changes we had to do with our earlier series of model, the Mercury 1 series. So we had to scale the training of the model, and the scaling happened not only in terms of increasing the data and the compute you throw at the model, but also in the core architectural innovations and the losses that were used to enable it to reason. Now, we have seen that with other models as well. Reinforcement learning is a key part of this picture. And when it comes to diffusion, reasoning with a diffusion language model has a number of benefits that you do not see with autoregressive LLMs. You can do reasoning in place. You can do reasoning not only to optimize the quality of the model, but you can also do reasoning to be more succinct and faster at giving out answers. So all of these different criteria, which are uniquely possible with the diffusion language model, were part of the innovation that went into bringing about Mercury 2.
Yeah, I would also add that I think diffusion and reasoning unlocks new capabilities for inference time scaling. If you look at how reasoning has been done in autoregressive models, usually it is typically by producing chain of thought tokens. So the model reasons out loud, thinks out loud, and justifies its answers. You can still do this with a diffusion language model. It is still a language model, so you can train it to do that. You can train it to output any sort of answer. But what's interesting is that the promise of a diffusion model is that you also have a new orthogonal axis along which you can spend inference time compute, which is the denoising axis. So you can spend more time or less time denoising an answer. And so you could, in theory, spend more time, which means you can have more ways, you can spend more flops producing a higher quality answer, which could improve quality. Or you also have the option of producing using fewer steps, and perhaps you could have noisier reasoning traces, but then you could produce them faster and produce higher quality answers in a shorter amount of time, or you could spend more time along the kind of length axis of reasoning and the sequence length axis, and that can also improve quality. So it's an interesting new opportunity that diffusion models offer, which autoregressive models do not.
Well, thanks for joining us today. I remember the first time we met in San Mateo at your office, and you walked us upstairs to the rooftop, and we took a look at it, and I was absolutely blown away by the demo that you showed. Obviously, we'd played with it before we came to visit with you, but we had really high hopes for the company, and you guys have certainly matched it so far. I think seeing the reasoning model come out was a hugely monumental moment in the company's success and journey, and it's been really really great being part of the journey and just working with you guys. And the partnership from the Menlo Venture side has been really, really amazing. And I just really appreciate working with you guys. It's just been fantastic. So thank you very much for coming today, and really appreciate your time.
Likewise, thank you, Tim.
Thanks.
Yeah, it was
Thanks for
amazing
having
to
us.
work with you. Yeah.
Thanks
Thank you for having us.